going sideways?
I would have brought my laptop, but it's still dead. I could have brought the whole DAC, I guess.
You brought it with your DAC.
We're close.
there you go.
We're close to
Booyah,
success.
you're good.
We can just scroll through it. It'll be fine. All right, scroll away.
Get expedient solution.
Oh, this will be great. All right, welcome to the wild world of PowerPoint presentations in PDF form and also hobby liquids.
Looks like
So this presentation is going to go over a couple different things. It's going to be a kind of a high-level overview, so anyone who wanted in-depth math, I'm sorry. So it's kind of two sections. The first is going to be of like, what are liquids at all? What is Tripoli allowing? A couple design examples. We'll have the obligatory safety slide. And then we'll go in more in depth in kind of the design of them. So there's many ways you can make liquids. So this is going to focus mainly on the hobby ones and not talk about industry scale stuff. So no turbo pumps. I'm sorry. All right, next slide. All right, so before we begin, a quick disclaimer. So I do not officially represent Tripoli. This presentation is not endorsed by Tripoli. Everything I say is my own opinion and or interpretation of what they've written. About me, I have my Tripoli level 3. I got it at this past Airfest. I'm a propulsion engineer, so the top engine is one that I worked on. It's a liquid oxygen and methane engine. And about 3 or 4 years ago, I started getting into liquids at the hobby scale. And then Tripoli started thinking about what it would take to allow liquids at launches. So they had a couple demo launches where they allowed a small, basically three teams to come out, and we did a presentation to the board, we did some static tests, and eventually were allowed to fly in a kind of controlled environment so they could learn, what are liquids. So the first was at Balls, and then the second one was at Airfest, so I flew at both of those. Real quick, picture credits. I have a lot of pictures in here. I have stolen all of them, and I have not credited anybody. So if you see a picture, I either stole it from the internet, I took it, or it was taken by one of those fine people. All right, next slide. All right, so real quick, super basic, what are liquids? So everyone is probably familiar with solids. You have a solid fuel and a solid oxidizer. You mix them together into essentially a really thick tube, and then you put that in a case with a nozzle, rocket motor. There are also hybrids. These have been allowed for decades at Tripoli launches. They keep that solid tube of propellant, but it's not the fuel and the oxidizer, it's just the solid fuel. And above that, you have a tank of liquid oxidizer. So that's why they're called hybrids. It's a mixture of liquid and a solid. And that liquid oxidizer has a little injector that sprays it down the central core of fuel, and it burns out. Moving on to liquids, it's kind of similar to hybrids. You still have that tank of oxidizer, you still have that injector, but you've finally gotten rid of that last bit of solid and replaced it with a tank of liquid fuel that also automatically gets routed to the injector, and that spot where the hybrid fuel grain was is now the combustion chamber. So in the hobby realm, you use nitrous oxide as the oxidizer. Hybrids use basically anything that burns for the fuel, usually some form of plastic. Liquids in the hobby realm also mainly use alcohols or some hydrocarbons. In industry, there's wacky stuff, but we're not getting into that. Next slide. All right, so one level deeper, this is kind of a schematic layout of a liquid, so it won't always be laid out this way, they won't always be connected this way, but most liquids will have these components. So you have some tanks, one for the fuel, one for the oxidizer. These are usually actually one component, which we'll get into later. You then have some form of plumbing to take the liquid to other components. You don't always need plumbing, depending on how integrated you get. You'll have some form of valve to start the flow of propellant. You usually don't stop the flow of propellant in the hobby realm. And then the valves lead to the injector sprays in, mixes the propellant, it burns in the combustion chamber, which is where the fire happens. There's a couple different cooling options, which we'll talk about later. Next slide. All right, so Tripoli compliant liquids. So anyone who's familiar with real liquids, Tripoli is allowing a very narrow subset. I don't have the whole list of all of their rules in the updated safety code, but the TLDR is it uses nitrous oxide for the oxidizer. For the fuel, it uses either ethanol or isopropanol, IPA, so either Everclear or rubbing alcohol. And then you can also have additives in the fuel, up to 30% other hydrocarbons or dissolved solids. They also allow up to 30% gasoline. I suspect the reason for this is a lot of people almost exclusively fly E85, which is 85% ethanol, with the remainder being gasoline. It's cheap and easy to get, so that allows that. The reason why they allow dissolved solids is just like solid motors have fancy colors, liquids can do it too. You can dissolve things into the fuel to change the color of the flame. For example, boric acid roach killer turns the flame green. Calcium chloride pool hardener turns it orange. There's also, I believe, a yellow, a red, and a purple. No one's found blue yet. If anyone finds out how to do blue, let me know. It's really hard. You can only use nitrous for pressurization, so no turbo pumps. There's some material restrictions similar to the existing rules, so aluminums, carbon fiber, select steel in locations, and also no active throttle control during flight. Most of these are unpowered once they leave the pad anyway, so adding throttle would be really complicated. One thing I will also say is hobby motors are not the same as industry motors. This goes, it's true for solids and hybrids as well. A lot of, if any industry people look at the designs, they might go, what is this? Why would you ever do it that way? Think of it more like, it's more of a model rocket that happens to use liquid propellant and not necessarily an industry engine crammed into this tiny little thing. So the way I've kind of interpreted what they have written for the updated rules is, it seems to keep liquids similar to existing hybrids, which makes sense because there's a base of operations already. People know how to handle nitrous at launches. So if the liquid flies exactly like a hybrid, it's kind of easy to integrate. If anyone's familiar with the Ratworks Tribrid, a lot of these liquids are very similar to that. Next slide. All right. So how do these even work? Nitrous is weird. If you had, a cup of nitrous, well, it wouldn't be in the cup at room temperature and room pressure, it would be gas. If you wanted a cup of liquid nitrous at room pressure, it would have to be at 185 Kelvin, which is minus something in Fahrenheit. Really, really, really cold. Luckily, the point at which nitrous boils is not constant. It depends on the pressure. So if you increase the pressure to 750 psi, it would boil at room temperature. So if you had a little tank of nitrous, it would be liquid with some gas on top at 750 psi. This is super useful because now we can use that pressure to feed the propellant into the engine. You don't need a pump, you don't need a separate system of like helium bottles and regulators to pressure feed the propellant into the engine. So if you had, let's say, a tank of gas, like compressed air, you open it up, all the gas rushes out. On that bottom plot, it would follow that red line. Pressure drops really quick. That's not very useful for a rocket because you want a constant pressure during the burn, or at least kind of close to constant. Luckily with nitrous, because it's at that boiling point, as you let liquid out of the tank and that gas on top of it expands, the pressure drops. The nitrous itself boils to repressurize that gas. So as you're taking liquid out of the tank, it's boiling to keep that pressure up, and it stays almost constant. It drops down to about 70% of your starting pressure at the end of once all the liquid's out of the tank, and then the gas drops out pretty quick. In technical land, this is called BAPAC. Some rockets have used it, Spaceship One used it. Hybrids also use this, so it's kind of standard. Next slide. But my cup of fuel doesn't self-pressurize to 750 psi, so how do you get the fuel? So what we do is we have what are called piston tanks. So you have a tank of fuel, there's a couple different configurations, but you have a cylindrical piston with a couple O-rings around it, and that nitrous pressure pushes on the piston and it squirts the fuel out kind of like a syringe. So the two main configurations we use is stacked tank and concentric tank. So in concentric tank, you have a smaller fuel tank inside of your nitrous tank, and the nitrous pushes on the top, and both drain out down to the bottom. This is convenient because both propellants come out the bottom, so that's where all the valves and engines normally live. It's easy to plumb to. The stacked tank, you have a piston in the middle of the tank, and as the nitrous goes out the bottom, the piston actually goes up and pushes the fuel out the top and down through some plumbing that you now have to add. So it has less parts because you don't have that tank in the middle, but you have to run some sort of propellant line somewhere down the whole length of it. All right, next slide. So, how do you load the propellant? Fuel is easy, you pour it in the tank. So this is a picture of Austin and Charles from Cat Rocketry loading up Mojave Sphinx. So it's a stack tank configuration. So you open the forward closure and you dump the fuel in. Once the piston's at its spot, the O-ring friction holds it in place. Yes, they are filling it up with WD-40. Yes, WD-40 burns. It burns perfectly fine. No, it is not on the approved list of Tripoli fuels. For concentric tanks, it's a little bit more involved. Usually you have to take them completely apart, but it's kind of the same thing. You push the piston to where it needs to be, fill it up with fuel, and then you have to attach the injector to it and then kind of reassemble the whole thing. Nitrous, that's when it starts to get dangerous, so we don't do that by hand. It's just like hybrids. The rocket's out of the pad. You fill it remotely. If you have an enclosed container and you fill up nitrous from the bottom, it just compresses the gas and then stops filling. So what do? You have a small hole in the top of the tank, and it lets the gas out as the liquid comes up. And then when the liquid gets to the top, it shoots out the side. It makes this nice visible vent. This picture is actually a hybrid, but it's the same thing. It's also a safety widget because if you happen to fill the tank and then lose all electrical control, maybe a squirrel runs up and like eats your wires or something, you can't dump propellant, you can't approach it while it's pressurized, but there's a hole in your tank. So if you just wait, depends on the size of the tank, for 5 minutes, an hour, it'll eventually leak. All right, next slide. So to fill it, you need some form of ground support equipment. So this is similar or exactly the same as some hybrid systems, not Hypertech, but anyone who's used Contrail or Skyripper, it's the exact same system. You have a nitrous bottle, it's upside down to get the liquid out. You have some sort of, usually a box with your valves in it. They'll usually have relays because a lot of the valves are nitrous valves which take 8 amps, and you don't want to run 8 amps through 300 feet of wire. So you usually have a relay to actuate the valve, and you have 2 valves. One fills the rocket, the other one is a dump in case it doesn't launch. You can dump the nitrous out, so you don't have to wait for that little vent to bleed the entire tank. You can do wired or wireless, so the box on the right is a wired box I made for the launch of balls. They put us 1,000 feet away, so I had to bring over 1,000 feet of Ethernet cable, and I have since switched to a wireless system. So the wireless system is one developed by HalfCat. It is an $65 RC airplane controller, and it talks to some kind of servo-controlled relays, and you can actuate valves with that. It's been super reliable for them. I will also say you do not want fancy software or computers. If you are a college team or something and you want to bring your laptop out and run an auto sequence to control the rocket, please don't. There's a lot of, software has a lot of bugs. There's a lot of failure modes with that, a lot of unintentional problems you can get into. So just stick with switches, keep it manual. You don't want to be like, oh, the computer's doing something, but I don't know what it is. Next slide. Cool, so how does it start? Solid's are easy. You put the igniter in and it goes. Liquid's a little bit more complicated. So you have to do 2 things. One, you have to open up those valves to get propellant flowing into the chamber. And then when it gets there, you need a source of fire to get it going. So on the valve side, there's a couple different methods. Ball valves, poppet valves, spool valves. We'll get into kind of the details on those later. So the ball valve picture it's just like an off-the-shelf ball valve from McMaster-Carr, and it has an RC airplane servo on it to move the handle to open it. So you can use that for actuating ball valves. The other valves usually need some sort of pneumatic control, which you can do some funky stuff with the nitrous to get those to actuate. And then for the igniter, most of them are pyrotechnic. So if anyone's familiar with hybrids, they have a preheater grain. So up at the top, they'll have basically a little hockey puck of AP propellant to get the hybrid going. You can do the same thing with liquid. So the one on the right is a liquid I have. It has basically the core of an Estes motor wrapped around the fill tube. So you light that, the black powder starts burning. When the propellants come in, the black powder's still burning, it ignites it and goes. What HalfCat does, it's called a cartridge igniter. They also use an Estes motor, but it is kind of that middle picture. It's up at the top. You take the Estes motor, you remove the clay nozzle and you put it in a brass, like section of brass plumbing pipe. And that is attached to the injector. So it's up out of the way, you can fish E-match up to it, and when you light that, it shoots fire down into the combustion chamber. So it's been super reliable. I'm not aware of any that haven't lit, so it's pretty reliable. There's also something called a spark torch igniter, which is similar to the cartridge, except instead of an Estes motor, it's another liquid engine, but really small. And that's a whole project in itself, and I would love to go down a rabbit hole, but we don't have the time. So it's a thing that exists, you can do it, but it's going to be more complicated. So you really need to fix the igniter in place. So I went through a lot of pain on mine because I had that chunk of black powder in the chamber. If it's not fixtured in there and the propellant hits it, it will just launch it out of the engine and it won't light. So that's not a problem with the cartridge igniter because it's up out of the way in the plumbing. But a lot of igniters, like up-the-throat igniters, are, I would say, they're usually bad and you shouldn't do them. A lot of college teams will do it. They leave the igniter to the last minute and they'll tape some AP to a stick and kind of zip tie it to the chamber, and then it gets fire hose out of the engine and doesn't light. So avoid that. If you're going to do something, really fixture that igniter in there or have a cartridge. All right, next slide. So launch operations, they're pretty much the same as hybrids. If you took the LCO, blindfolded and said it's a hybrid, it would work fine. So you load the fuel during assembly, put the rocket on the pad, fill nitrous remotely, you launch it. If it doesn't light, you dump it. So I haven't done a lot of hybrids and liquids at normal launches, but from what I've seen and heard, kind of the normal procedure is because you have your own custom GSE, usually you're the one flipping the switches. So what I like to do is we talk with the LCO first, be like, this is what I want to do. You do this, I do this. If they want to change something, good. Just talk it over, make sure everyone's on the same page. So flyer controls the GSE, LCO reads the flight card, tells you go for fill, you start filling. When it's full, you say, I am ready, and then they'll be like, 3, 2, 1, and then you push the launch button off close. All right. Finally, we're going to start looking at actual liquids. Next slide. So there's no kind of defined categories for liquids. There's like one defined category, but I've noticed that a lot of them tend to fall into 2 camps, so I've arbitrarily named this one the integrated vehicle. It's probably what a lot of people think of when you say liquid. It is the propulsion system is the rocket is the propulsion system. It's not like a model rocket where you put the motor in. The whole thing is the motor. So if there's any solids brain rot people out there, it's similar to submin, where the motor case is the actual rocket. So in both of those, the outside is the tank. They can be stack tank or concentric tank. The one on the left, I believe, is a stack tank. The one on the right is a concentric tank. You can put the valves and plumbing either inside the tank or outside the tank. What a lot of people do is usually the fin can is where they'll cram all the valves in the engine plumbing down at the bottom. And then the recovery is usually built into the nose cone. As you can probably guess, they're mostly high performance designs because it's all motor. So these usually go very, very high and very, very supersonic. Next slide. So this one would also kind of fit into the integrated vehicle, but it's so ubiquitous that it gets its own slide. So this is the Mojave Sphinx from Half Cat Rocketry. So they have literally wrote the book on this. So they have done what a lot of people wish people would do, is they made a fully open source liquid, and it's not just some set of plans on a website from 1995. It is like 300 pages of drawings and documentation. It has everything you would need, not just for their rocket, but for stuff in general. There's like O-ring sizing guides in here. It's a great resource. So on this rocket, the design for manufacturing team 1, it is not high performance, it's not aerodynamic, but it is very, very easy to build. So there are some lathe parts, but you can build this with a lathe and a hand drill. So it's incredibly simple. It's very, very easy to modify, and it's a great kind of first project. It is a little big. It's about an M, big L, small m impulse, but the bigger the liquids are, it's easier to work on because the parts are larger. You can get your hands in it. It's not tiny and fiddly. All right, next slide. So my personal favorite, the monotube. So these ones are exactly like normal solids and hybrids. It's a tube, you put it in the rocket, fire comes out. I have one right here. It's not done yet. So you can make your own tanks for this, but what a lot of us do is you just use solid motor cases because they exist and they're already rated for pressure and they already fit in rockets. So this one's in a Aerotech 381080 case. They are a little bit harder to build just because you have to fit all the valves and stuff inside of a tube. So this one, you have to fit all the valves and plumbing, if it exists, inside of an 1.5" diameter tube, which is kind of hard to do. So it's a lot more tightly packaged. There's a lot of different ways to build valves, and in the monotube style, you will see a lot of variation in how valves are built and how they're integrated. If you like puzzles, they're a great puzzle to solve. So the ones on the slide, the kind of upper left is mine. It's called Tiny Liquid. It's a 24mm F motor. The one on the bottom is a 29mm G motor. And the upper right is a 54mm that was built by Ryan Callahan of Keg Rocket fame, flying in the Liquid Goblin. So 54 is a great starting size. It's big enough that you can kind of fit valves and stuff around. You can do 24, as evidenced by that picture. 18mm is theoretically possible, but it's going to be, you know, annoying. All right, obligatory safety slide is up. All right, so a lot of this applies to liquid or to hybrids as well. So one of the main safety mitigate or hazard mitigations is standoff distance. So when it's pressurized, it's really far away. So if it blows up, it's way over there. There's no one near it. No one's going to get hurt. So anytime it's pressurized, everyone needs to be evacuated to a safe distance. So back to the flywheel. I did the math as not an excuse. Nature will find a way. Oxidizer safety, so you are near part of the system when it is pressurized, and that is the plumbing from the fill bottle, or from the nitrous bottle to your fill valve. So sometimes the valves are on the bottle, sometimes there's a short flex hose, but that will be pressurized because you have to physically open the bottle. Because of that, all of that plumbing needs to be rated for the pressure, it needs to be cleaned for oxidizer service. There was one more thing. Oh yeah, and material compatibility. Please don't make it out of rubber. It's an oxidizer, it will burn. You should also have personal protective equipment, so I like to wear a full face shield. Some people just wear safety glasses. I have normal glasses, so I like to wear a full face shield. Also, a full face shield will make your face hurt less if you take a flex line to the face than safety glasses will. So I like to wear a full face shield. You want leather gloves when you're actually doing stuff with the nitrous. As it comes out of, you know, if it leaks, it expands and gets very, very, very cold. And you can get frostbite burns pretty easily, so wear leather gloves. And then you want to wear natural fiber clothing just for general fire safety. So, you know, if you light on fire, cotton will char and burn away, but synthetics will melt into your skin, and then it needs to be removed with a wire brush at the hospital. Another thing I like to do is I will wait for other people to leave the pad before I open the nitrous bottle, just so they're not wandering around a pressurized nitrous system. So I'll let everyone leave, then open it, fall back, launch, go out, turn off the bottle, then go get the rocket. Fuel safety is a lot more easy. There's not a lot of difference between the fuel in the rocket and the fuel in the gas can on the ground. So, you know, don't be an idiot, don't smoke near it, don't splash it in your face, that sort of thing. I like to wear eye protection when I'm disassembling the rocket. All the fuel should be gone, but I've noticed on some of mine, there's a little bit of fuel left over in part of it. This is kind of specific to my design. I won't get into the details, but because of O-ring friction, it can store like 5-ish PSI. So when I pulled it apart once and some fuel kind of spurted out, I'm like, oh, that's interesting. I'm gonna make sure I always wear safety glasses so I don't get sprayed in the face with alcohol. All right, next slide. Oh yeah, perfect. We're now getting to the math part, right? Everyone's excited for math, calculations and sizing. Next slide. I lied, we're not doing math. It takes too long. So I thought about doing like, you know, a whole like procedure for doing the math for the design, but that's a whole nother hour. So I'm not going to go into it. I will say, if you do want to get into it, it's in the half cat book. It's also, you can go pick up NASA SP-125. It's free online on the NASA Technical Report Server. It's how you design rocket engines. It has all the math, all the useful stuff. It's a great read. So if you did want to go and do all the math yourself, you could pick up H&H. You could go to NASA CEA. It's a nice little website. It does all the chemistry. You don't have to do any chemistry. You say, I have this fuel and this oxidizer at this pressure and mixture ratio, and it will give you the gamma and the gas temperature and all the pressures. It does all that for you. The NIST website has a thermophysical properties of fluid system website. It will give you any property of any fluid you could ever want. And then you take all of this and you shove it into Excel or whatever, or MATLAB or Python, and then you can do the math. And the reason why you want to use a computer program is you will not get it right the first time, and you'll have to do it hundreds of times. And it's easier to just hit go than to do it all out by hand with pencil and paper. Next slide. Or the easy way, HalfCat has already thought of this, and they've made a great sim. So solid motors, you don't do grain regression stuff by hand. You use Burn Sim or Open Motor or something. HalfCat Sim is an Excel-based tool. It does all of the design. You put in your inputs. I want a tank this big. I want a throat this big. It will tell you the thrusts, the pressures. It's set up for nitrous. It has a bunch of different fuels you can select. It even exports it into a format where you can throw it into OpenRocket and simulate it. Also, importantly, it's anchored with test data. So nothing ever goes the way you want it to when you're doing math. Theoretical is great, but reality will disagree. This has been somewhat anchored with test data, so people will design motors with this. They will fire it and be like, oh, well, when I fired it, the discharge coefficient was 0.4 instead of 0.5. And you're like, oh, cool. I'll note that for later. All right. Next slide. How are we doing on time?
6 minutes.
Okay. I'm going to breeze through this one really fast. It's mainly just the operating, when you're doing the design, this is numbers you should target. It takes forever to go through. It's a bit of an eye chart. But in general, you want to stick to kind of 200 to 400 PSI chamber pressure. At least that's where most of them fall. You can go lower. I've gone down to about 100. You can't really go higher because you're limited by nitrous pressure. One reason to go lower is the heat flux gets lower, so your engines can run for longer usually. Mixture ratios, usually in the 2 to 4 range, which is rich. You want to keep the flame temperatures cold. For injector pressure drop, so the injector needs some amount of pressure drop across it to be stable, just because there's little pressure fluctuations as it's burning. And if there's no pressure drop across the injector, those pressure fluctuations can go back into the feed system and do that. So you want some pressure drop. It's usually given in percent of chamber pressure, dP over PEC. So it's 15%, usually a good number to not go below unless you really know what you're doing. A lot of people end up, go for 50 just because if you have 50% pressure drop and your math is off a little bit, it will be 40% instead of 5%. Doesn't really matter because a lot of the time if you have 100 PSI chamber pressure, your tank's at 700, you're going to have a lot of pressure drop, so it doesn't care. Chamber dimensions, there's a bunch of stuff, but the throat diameter is kind of the main one that's important. It sets all of your other dimensions. L-star is a made-up thing, but basically, we use it as kind of like a shorthand for how long propellant's in the chamber. So it takes time to burn, especially nitrous. It takes 3 to 5 business days to do anything. So basically, the L-star is just, you want the chamber to be long enough that it'll actually burn. If you make it too short, it will not burn, and you can have it unignite, and it's a sad day. Contraction ratio just basically sets how big around the chamber is. You usually want to start at a contraction ratio of 4 is a good starting value. You can go lower if you want. You can go bigger too. Reason to go bigger is if you can't fit all your injector stuff, you can just make the chamber bigger. It won't hurt anything. All right. Next slide. All right, so the math stuff is great. You can do the math. It will be, if for one set of math, here's my liquid, all the math, there's 100 different ways to build that. So this is kind of the fun part where you get into the really kind of the fun puzzle part of design. All right, next slide. So start with the easy part. This picture is from the HalfCat Mojave Sphinx, so it's kind of an exploded view of the tank. It's basically a solid motor case. It's an aluminum tube. It's not that complicated. So it's aluminum tube. There's some, closures that have little O-ring piston seals around them. They go in the end. In concentric tanks, the fuel tank inside is just another tube. For custom stuff, cutting threads is usually pretty hard unless you have a lathe. So a lot of the custom tanks we use radial bolts, so you can just buy an aluminum tube, make your closures, they go in, and then as you can see in this, you just put the bolts radially. If you do that, you can't easily put it into a motor mount because the bolts stick out. So a lot of this is kind of integrated vehicle, you know, the rocket is the tank type thing where it doesn't matter. Other options, you can use snap rings like Loki and Contrail, or threads like Aerotech. But again, you need a lathe to make those. When you design it, you should size the thickness to hold the nitrous pressure plus whatever safety factor you need. So the nitrous, you know, on a hot day can get a little over 1,000 psi, so you want to take into account all that. When you're doing the number of bolts, which the half-cat sim also has a tank designer, so they do all the stress calcs in that spreadsheet to figure out how many bolts you need. You usually kind of want the closures to blow up first because it will usually make less of a mess than unzipping the entire tank. You'll need some sort of ports on the end to get the fluids out. You can use NPT, I hate it, but it's easy and simple. Another thing you can use is they make sealing washers, which are these nifty little things. It's a metal washer with an O-ring in it. So you can take a straight thread fitting and instead of cutting like a AS5202 port, you can just put a washer on it and screw the fitting in and then it seals. A lot of the British teams use it and they've successfully converted me. The piston is also super simple. It's just, it's a cylinder of metal with 2 O-rings on it. You usually hollow it out to make it lighter. You could also make it out of Teflon, which I've done on the smaller scale stuff just for mass reasons. All right, next slide, everyone's favorite subject. It's the best. Valves, everyone hates valves. They're the worst. So there's many different types of valves, and there's many different iterations of these types. So this is just a few that I doodled up in PowerPoint real quick. So ball valves, everyone has probably seen and touched a ball valve. There's a little ball, there's a hole drilled through it, and you turn the handle 90 degrees. It aligns the hole or unaligns the hole to start and stop the flow. There's some valve seats shown in green. They're just little plastic donuts basically, and they push on the ball and they seal on the side so the fluid can't go around the ball and bypass the hole. You usually don't make these. The ball and the seat is a really high precision part, so unless you have like a really good machine shop, you're probably not making a ball valve from scratch. So usually we'll buy one that's somewhat lightweight and then put an actuator on it like that RC servo to actuate the ball valve. The other valves, usually these are all custom, like this little guy is a tiny, tiny spool valve that I made. So the poppet valve, there's kind of like, it's on top there's a green part, that's a seat that's usually made out of some sort of soft plastic like nylon or Teflon. And on the bottom, there's a pneumatic cavity, which is how you actuate it. And then there's some O-rings in orange to separate those two volumes. You apply pressure to the bottom, it shoves the poppet up, and it seals against that fluid inlet at the top. When you vent the cavity at the bottom, the fluid inlet, or the fluid at the top pushes the whole poppet down and then flows out the side. Spool valves, they don't have that poppet seat, it's just all O-rings stacked on a cylinder, and then there's a bunch of holes on the valve body, and as you move that cylinder back and forth, it will align different sets of holes to allow fluid to flow or not flow. These are usually somewhat tricky to design. Where those holes come in, it usually makes a sharp edge, and as the O-rings go across it, you will chop the O-rings and they will die and will be sad. So there's some lead-in stuff you can do to make it happy, but they're kind of tricky to design sometimes. You can also, nifty thing with spool valves is you can stack the fluid section. So you can have one just really long, spool with a bunch of O-rings and actuate a whole bunch of different fluids all at once. You can also put a poppet on the spool valve. There's an infinite number of combinations. All right. Next slide. Guess what? More valves. So solenoid valve, you usually don't fly these. They're big and heavy and take lots of power, but they're used in the GSC a lot. So it's kind of like a poppet, except there's a solenoid coil around it. When you energize that coil, it makes a magnetic field and lifts the poppet up, and the fluid kind of comes up and around and flows out. So if you've ever used nitrous valves, that's what they are. So the NOS valves that we use in the GSC, it's just a solenoid valve. Check valves are one-way valves with air quotes because they like to leak a lot. But basically it's just a metal or sometimes rubber ball that a spring pushes into a seat. If fluid comes in one way, it pushes the ball closed more, and if it comes the other way, it opens the ball valve up. So you can also use the spring to control what's called the cracking pressure, which is the pressure required to open the valve. So you can do funky stuff with it. And then the headache meme I had to include because valves are notorious. Like if there's a problem with a rocket, it's usually a valve. All right, next slide. Kind of like a valve is the GSE interface. So earlier, we talked about there was that nitrous line that goes to the rocket to fill it. You don't want to leave that connected because you'll take your tank with the rocket as it takes off. So you need to disconnect that line somehow as it launches. So there's a couple different ways to do that. The one that's used on half-cat, it's kind of neat. It's a two-piece piston seal, so that you can see on the QD, it's two pieces. One goes inside the other with an O-ring, and the pressure wants to blow that apart. But what they have is a little plastic clip that goes around some flanges on the outside to hold it together. That clip is tied to a string, and that string is tied to the launch pad. So as the rocket launches, it pulls the clip off, and the residual pressure in the line blows the QD apart. Any hybrid people out there will probably recognize the UC valve. It lies, it's not really a valve, it's a plastic tube, and you light it on fire, and then the tube is no longer attached. So it's super simple because, again, it's a plastic tube. Usually you have some sort of preheater grain that burns through it, so you can fill nitrous through it, light it. When it comes off, nitrous automatically starts flowing out. You can use this, so in my example, I actually flow the main nitrous for the engine through that UC valve, so when it comes out, it starts, burning with the fuel. You can also use the UC valve as a pilot for the poppet valves because they need that little pneumatic cavity. So you can use the UC valve as you're filling. You can branch a little bit off to that poppet valve to hold the poppet valves closed. And then when the UC valve bursts, it vents that cavity, the poppet's open, and then your main injector starts flowing. And then the last one has only been used by one rocket, I think, but it's really neat. It's the Sunride QD. It's from a UK team. It's kind of like the half-cat system, so you have that two-piece QD, but it's vertical and on the bottom of the rocket. So the fill line section is attached to the rail. There's a little bracket that slides down the 80-20, you tighten the bolts. And the other part is on the rocket, so it kind of sits on top, and the rocket is heavy enough that the pressure doesn't blow it apart. So there's no separation system, it just sits there, you fill nitrous, and when the engine lights, it just takes off. Next slide. All right, injectors. So this is, it injects the propellant into the combustion chamber. So the pressure in the system goes from highest to lowest. So you have your tanks are always the highest pressure, the chamber is always the lowest. You want some pressure drop across the injector for stability. If you start going near 20%, think about what you're doing, but you're usually above that anyway. The injector has a big influence on engine efficiency. It's, you're mixing the propellant, how well you mix it will factor into how well it burns. So nitrous, it's really hard to get good efficiency because it takes forever to burn. So when you inject it, if anyone's ever taken a CO2 fire extinguisher and shot it, it expands, makes that, cloud of cold gas. Nitrous is doing the same thing. So when it gets injected into the chamber, it expands, gets really cold. You have to take that, heat it up, turn it into a gas, decompose it, and then it can burn it. And all the while, it's going down the chamber. So you need to have either a really long chamber or somehow make the nitrous go sideways and do weird recirculation zones and stuff like that. So normally we can only get 60 to 70% combustion efficiency out of nitrous engines. If anyone's in industry, you will know that it's absolute trash. But it works well for what we do. On the actual injector elements, so usually you have one type of element and you cluster a whole bunch of them, so you can kind of see on the side, there's a couple different styles of element. The top ones are all known as impinging, so you have different, numbers of holes all shooting together and they slap together and mix. The water flow test is the outer elements of the pentad being tested, so you can kind of see how they shoot in and mix together, and then in the real one there'd be another stream in the middle coming in. Shear coaxial is a tube in a hole, so one propellant goes through the tube, The other one goes through the annular gap between the hole and the tube, and they come out at different velocities, and the shear forces mix them. And then lastly is the pintle. Usually you don't cluster lots of pintles, you just have one big one. So it's kind of like shear coax, where there's an annular gap, but instead of having just a tube, it has this enclosed pintle with holes or slots on the side. So one propellant gets shot out sideways, the other one comes down in an annular sheet, and they kind of interface and mix. How you do the number of holes or slots at the bottom gets into kind of black magic. Manifolding is kind of tricky to do because you have, all these elements, they need to get different propellants, and how you do that depends a lot on the element type. If you're doing 3D printing, like the Pentab, you can get really weird inside and have all these funky passages, but you don't always 3D print the injector. So what a lot of people do is what's shown in this half-cat injector is you cut a really deep slot into the injector, and then you have, a ring of holes that all talk to that slot. So if you have one propellant port, it'll distribute, like in this case, the fuel all the way around and feed all those holes. While we're talking about this, shout out to the Sprintle. This is an injector half-cat came up with. It is unique. It's not the best, but it's mostly consistent. So drilling all of these angled holes is evil because doing angled holes is hard, and they're usually like a 32nd of an inch or something really tiny. So in the half-cat injector, they're all axial, which doesn't mix at all, but they put a giant flathead screw in front of the nitrous, so it hits that screw and goes out sideways. So it acts kind of like a pencil, but with a screw, hence the Sprintle. All right, next slide. All right, the combustion chamber is where the combustion happens. So it's a tube. There is an injector at one end and a nozzle on the other. These can all be one component. They can be two components. They can be three or more. There's lots of different ways to build it. But basically, it's where the fire happens. It needs to be long enough that the nitrous and fuel can burn. And when you're designing it, a lot of these get hot. So be sure to avoid that. Your material properties are usually a lot weaker when it's hot, so your 6061 is not 40 KSI, it's probably 15. So because there's fire on the inside, you have to cool it somehow. There's a couple different ways to do that. The first one is called heat sink cooling. It's really simple because there is no cooling. It's a block of metal, and you just fire it long enough to not melt. So there's some tricks to designing this. So on the heat sink example, it's the Mojave Spanx chamber. You can see the walls are pretty thick. That's not really for strength. That's just because you're sinking the heat into the aluminum. So you need more of it to soak the heat up. You want something thermally conductive, so instead of just heating the wall up to 80 billion degrees, it gets distributed throughout the part. If you do this, the throat is the hottest part. It will usually die first. So one thing they do is they have different inserts. So pictured here is a copper insert. They've also used graphite. So you put that in there and it will kind of take more of the heat. So you need a higher temperature material. These usually run for single-digit seconds depending on your chamber pressure and OF, but most liquids only run for single-digit seconds anyway. The most they've done, I think, is around 7 or 10, but that's pretty low pressure and pretty rich, so the flame's cold. Ablative cooling is kind of similar to solids. You put the fuel grains into that phenolic tube and put that in the motor case. If you have just the phenolic tube, it will protect the chamber. So it will char and ablate and protect the aluminum. Oh.
That's all.
Time's up. Damn. Anyway, so usually you don't do an ablative, you don't make your own ablative nozzle. Usually with ablative chambers you get like a graphite nozzle and just have an ablative tube because you can buy a phenolic tubing. You could do an ablative nozzle if you buy like Aerotech nozzles from RCS Motor Components. There we go.
We're back.
Cool. Regenerative cooling is probably beyond the scope of this, but some people have done it at the hobby scale, so I threw it on there anyway. This is what big boys use. You have tiny passages through the walls of the chamber, and you flow one or both, hopefully in separate channels, of the propellants through these channels, and they cool the chamber down. You can machine them. There are ways. a lot of people just 3D print it because there's some cheap 3D printing places out there, so you can get a chamber for a couple $100. The downside is depowdering those channels can be really hard because the 3D printing process will leave powder in them. Also, the typical OFs that nitrous engines run at like to be really high, and there's not a lot of fuel for cooling. And no one really wants to cool with nitrous because we don't know what it's going to do. That'll probably blow up. Lastly is film cooling. So, you have your clusters of injector elements. You can also have a ring of fuel-only elements around the edge of the chamber and shoot fuel down the walls and make a kind of a cool boundary layer to protect the walls. Usually use this combined with something else like regen or ablative, just to, like if your regen is looking like it might melt, you can put 5% of the fuel down the walls to help save it. This picture is from Armadillo Aerospace. They actually did 100%. It's all film cooling. Their engine was just a stainless tube that they spun the throat on, and they fire hosed 30% of the fuel down the walls, and it worked. It's not efficient, but it's incredibly simple. All right, next slide. All right, so putting all the bits together, we've talked about chambers and valves and all this stuff. There are 100 different ways to do it. There's no one way, which is why I don't have like a tutorial. But now you put this here and that there. There's too many ways. So kind of the first fork of the road is to monotube or not. Monotube is nice because you can, your motor's in a tube. And if you have a rocket, you can put it in. And if someone else has a rocket, or if you want to fly it in a different rocket, you can put it in a different rocket. Integrated vehicles lock you into one rocket, so if you want to fly the liquid, you're flying that specific liquid. There's always exceptions to all these rules, but there's no right design. You can optimize for whatever or not. But like, for example, like on the Mojave Sphinx, it has easy access to everything. So you can get your hands on the valves, you can get your hands on the igniter. It's easy to get to. On monotubes, they're much more tightly integrated. So in this example, there's a check valve inside of a spool valve, which is inside of the injector, which is inside of the tank. It's a little bit complicated. If you're not already good at design, I would definitely recommend something like a Sphinx over a monotube. Monotubes can get very complicated. Also, when you go to design this stuff, it won't be right the first time. Just like you have to do the math a lot, you have to do the design a lot. So sometimes you'll take your math, you'll start designing it, and you find out your valve doesn't fit. So you have to make this part bigger, that part bigger, and iterate. And just, I want to say, don't be afraid to iterate. If everyone does it, it's a normal part of the process. All right, next slide. All right, so now I've rambled for like an hour. I've given you the first 2 circles of the owl. You must now go forth and draw the rest of the owl. For the next step, I would recommend reading the Half-Cat book. It has far more information than I can ramble about in an hour. It's over 300 pages. Even if you don't want to build a Mojave Sphinx, it has a bunch of like the basic info that I've gone over. It has a whole lot more. It's a great resource for just general, how big do I make this O-ring groove? Well, it has it in the book. That being said, a Sphinx is a great first project. It is big, but again, it's easy to work on. Also, it's an M motor. The per flight cost is about $60. So you'll spend about maybe 5 M reloads worth building it, but then $60 per flight cost is pretty good. You don't need a lathe. It helps. Like I have a lathe at home now, and I can just go and build stuff. But if you don't have one, that's fine. SendCut, Send, PCBWay, JLC PCB, they all offer CNC machining. Some of them have 3D printing. So you can design stuff, send it out to them, they'll build it for you. I'll also say, if you have a plastic 3D printer, that's super useful. You can print drill guides. So you can print a block with holes at specific angles, you can put your part in, and then if you have a hand drill, you can put it in a vise and drill your holes, and now they're precise-ish. But you can do a lot with a hand drill and printed drill guides. You can also use existing parts. So like, I'm using an Aerotech case for my tank. I could make a tank, but this exists, it's threaded. You can use it. You can use you could use a contrail tank for hybrids because they're already long. You could use a low-key case for the chamber. Half-Cat has kind of hinted at it. They're kind of working on a project like that, so it uses all existing parts. For some resources, Tripoli.org, of course, they'll have the updated safety code. If doesn't match anything I've said, definitely go with what they said. I'm just going from memory mostly. Half Cat Rocketry has their book. It's free as a PDF. It has a bunch of their other projects. They have cable cutters up there if you want to do, you know, single point dual recovery. And then a lot of the solids people always say find an in-person mentor. There's not, if you want to make solids, there's not a lot of those for liquids, but the r/Rocketry Discord, if anyone does Discord, has about 8 billion liquid projects on there to learn from. Some of them are bad, some of them are good, but it's a great resource just to see what other people are doing. Like this valve I didn't come up with. Someone else had a valve in 54. I'm like, oh, that's neat. I think I can make that smaller. So it's a great place to go. I think that's it. Perfect. We don't need to go there. All right, so that's it. Any questions?